Design considerations. Basic function of a PCB is to provide support for all circuit components and to interconnect the component electrically. Design and layout considerations must also address relation between interconnection of components and the assembly of the system. PCB design considerations. Mechanical considerations, electrical considerations, mounting method. Types of board. Design consideration must consider board types for the design. Mechanical considerations. Important design requirements include size, shape and weight, location of the component and their mounting, dimensional tolerances, shielding and equipment marking. Mechanical support and connectivity of components mounted on it. Single-sided boards. Mostly used in applications where cost is to be minimum. When designing layouts to jump over conductor tracks, either components or jumpers are used. Double-sided boards. These types of boards are made PTH or without PTH. PTH boards are expensive. It is used in circuits which are complex. Components and holes should be minimum for reliability. Mechanical design considerations. Optimal board size should be compatible with the PCB manufacturing process. Position of board mounting holes, brackets, clips, clamps, and shielding boxes. Proper fixation arrangement of heavy components. Proper hole diameter for hole mounting. Assemble board to withstand the mechanical stresses. Vibrations occur in transportation. Types of installation of boards. Method of cooling. Specific location requirements of the components. Component area. Component of area is calculated by contribution of single component. Dimensions of the component are measured from manufacturer catalog. Volume computing. Volume available for an electronic assembly is calculated with care. Actual volume is important to know that the maximum volume that the board can occupy under worst conditions, including the safety clearness. Acceptability and adjustable components. Adjustable components are variable resistors which is used in printed circuit board assemblies. These components should be mounted on PCB in such a manner that there is an easy access to such components. Horizontal and vertical mounting components. Axial components are mounted either horizontally or vertically. Vertical mounting takes less area, but it has a disadvantage of lower reliability and difficulty in mounting the components. If the area is limited, volume also will be limited. In such cases, the board height should be greater than the axial components. Board size. The problem is in designing a board is that the large size boards are required more space for interconnection. Small size boards leads to high cost. Location constraints for board size. Connectors, fixtures, adjusting devices. Geometrical constraints. Locating holes, mounting holes, edges, locating holes. Center should be 1.5 times of the hole diameter from the edge of the board, but not less than 2 mm. Safety area should be around in a circular form. Mounting holes. Safety areas are needed to provide around the fixing holes, keeping in view size of the screws, unless insulating washers are used. Edges. 2 to 5 mm safety strip is provided for all edges. It is important because trimming of the boards causes delamination of copper areas too close to the edge. Partitioning. Minimizing the number of interconnections must reduce the size of board. Partitioning done in different levels for reduces interconnections. Advantages of partitioning: easy layout design, easy manufacturing design, easy maintenance. Electrical considerations: its requirement have such parameters as circuit functions, wiring distribution, and component selection with respect to electrical rating and size of the component, internal and external interconnections, and tolerances. Conductor dimensions. Conductor width is determined by component packing density, minimum spacing between conductors and components, general constraints due to component outlines. Resistance. The copper printed tracks on PCB has a finite resistance which introduces a voltage drop is proportional to the current flowing in particular conductor. Capacitance considerations. Capacitance is an important parameter to design a PCB at high frequencies. Capacitance between conductors and opposite sides of the PCB. Capacitance between adjacent conductors. Inductance of PCB considerations. Important concern for fast signals and high-speed logic circuit. Logical circuits operate at 10 kHz. High electrical stresses. Increasing level of integration increases stress of electrical. Increasing density of interconnections in printed circuit boards demands the design progressively decrease spacing and size of the conductor parts. Important design elements. PCB designer must consider these elements for design: types of circuit, board size, number of layers, pad stack sizes, hole sizes, layer thickness, board thickness, external connections, mounting holes, supply and ground layer thickness, component details with specifications. Important performance parameters: tensile strength, flexural strength, shock and vibration, thermal shock, warp and twist, salt spray, dielectric breakdown voltage, solderability, insulation resistance, flame resistance, conductor temperature, high altitude considerations. PCB design rules. Design rules for analog circuits. Component placing. Components which need access from front place have to be placed exactly according to the instruction of the equipment of the designer. The same applies for all connectors and any other connection to PCB components for internal adjustment such as potentiometer, trimmers, switches, etc. Components should be arranged near board edge and oriented in proper direction. Access of the components should be free, not obstructed by other components. Metal case components should not be placed near the path that is needed. The placing of heat-producing and heat-sensitive components must be carefully planned. The direction of airflow in the equipment has to be known. The airflow should have free and unobstructed path via the heat-producing components. Heat-producing components are regularly distributed over the entire board area as far as it is feasible. This is to avoid a locally overheated board. Hot components have to be separated from the board surface by suitable spacers. The locating heat-sensitive components must avoid a close proximity to hot components as well as a place in a flow of already warmed up air. Components holes always placed in grid intersections to take care of standards, lead spacing from the components as well as NC drilling requirements. Signal conductors. General. Signal conductors in layout have to fulfill a variety of different tasks. Length of signal conductor should be made as short as possible. Because magnitude of undesired inductive and capacitive coupling effects increases more or less proportionally to the length of the particular conductor. Signal conductor layout has to be done particularly carefully for the following types of circuits: high frequency amplifiers, oscillators, multi-stage amplifiers especially with high power output stage, feedback amplifiers and regulators with remote sensing lines, high gain DC amplifiers, amplifiers having low level signals, high gain DC amplifiers, amplifiers handling low level signals, precision differential amplifiers, high frequency amplifiers. Electronic circuit designers design a circuit with a high frequency, above 10 MHz. It is easier to build up oscillator than an amplifier. In designing of layout of an oscillator circuit, problem will arise with the result that the oscillator does not oscillate at the desired frequency. To avoid this, layout should be carefully designed with reducing coupling capacitance between signal lines to the maximum extent. Voltage amplifiers, especially with high power output stage. Large current drawn by high power stage will flow through the conductors with own resistivity R. Additional resistance may come also from improper solder joints. It will affect in modulating voltage and ground of input, resulting in low frequency oscillations, which is called motor boating effect. To overcome the decoupling of power supply conductors with sufficiently large capacitors must be done. Separate voltage and ground conductors can be provided for two different stages so that there is no common supply or ground path. Feedback amplifiers. In designing high wattage power supplies, example with regulation 0.01 to 0.1%, considerable care in PCB layout design as well as planning of remote sensing line to front panel is necessary to meet regulator factor. Correct PCB layout can solve difficult situation in feedback amplifier circuit design. If the output is not properly sensed to give a feedback straight from the final supply output point, the resistivity of conductors, although very small, will cause a poor regulation. Rectifier capacitor circuit must be connected to star point for good circuit performance. When a device is soldered onto the PCB, thermocouple junction is formed between copper. If temperature gradient exists, then different junction will create different voltages. It affects the noise signal to amplifier. A possible solution is to put the input stage into a separate enclosure which does not allow a free movement of surrounding air. Amplifiers handling low-level signals. This group of amplifiers can be divided into amplifiers for signal with high impedance, low currents in an NA range, low impedance, low voltage in an NV range. Supply and ground conductors. Ground lines. Analog and digital circuits on the same PCB should strictly have independent ground conductor networks. There is one or more type of circuit part which should be provided with separate ground conductor. Reference voltage circuits are in particular sensitive to ground potential fluctuations because the difference voltage between an input and reference is amplified to drive a switching device. The ground conductor systems are connected together in the most stable ground reference point of the equipment. Supply lines. It has to be provided with sufficient width to keep resistance and inductivity low, while capacitive coupling to the ground gets increased with more width. Supply lines are connected to the circuit end with the highest signal power level. Power consumption along the supply line is decreased. Reference voltage circuits should be taped the supply line directly at the input to PCB in critical cases and even externally at the most stable supply point. General rules for design and analog circuits. Keep the signal path as short as possible. Provide the separate digital and analog grounds and tie together only once. Provide connection between system ground to actual earth ground. Connect capacitive shields once to provide a return path to the noise source. Metal should not be left electrically floating. Limit the bandwidth of the system. Between two PCBs, use twisted pair cable to improve the noise rejection of the system. Design rules for digital circuits. The four main problems that can affect digital PCBs if not properly designed are reflections, crosstalk, ground and supply lines, electromagnetic. Reflections. Rise time of ICs, the conductors cannot be considered as short circuit but must be looked at as pieces of transmission lines. Transmission lines are normally mismatched on both sides. Multiple reflections take place based on particular value of wave impedance of conductors. In PCB designing, PCB connectors and interconnections should have proper impedance value. Proper impedance value which reduces more reflections. The desired impedance value based on signal lines and ground lines. Large impedance value are called as thin signal conductors. Small impedance value are called broad signal conductors. Digital circuits must have low frequency signals which is used to reduce reflections. Crosstalk. If two signal conductors run parallel to each other for a length that exceeds roughly that time crosstalk occurs, and pulse edge on the conductor will induce a short spike or even a train of pulses on the neighboring conductor. The main point for designer to remember is that for keeping crosstalk low, have to keep impedance as low between signal conductors and ground. A ground conductor running between two signal conductors on the PCB side will almost eliminate crosstalk. Ground and supply line noise. Two important measures for PCB layout. To have low impedance between power supply line and ground line obtained by having a broad power supply conductor and a broad ground conductor sitting right across each other on opposite sides of double-sided PCB. By providing an electromagnetic ground conductor or at least a ground mesh, finally leaving the copper in all unused parts of the PCB. Remedial measures of PCB digital design. Provide well-known decoupling capacitance. Provide a low wave impedance. Provide ground with a large copper surface. It gives good electromagnetic coupling with ideal grounding point and make it difficult for ground to be moved up on voltage spike by a current edge. A closely knit grid of bred ground conductors ideal for PCB digital design. Conductors which provide ground and voltage connections between power supply and individual PCBs should be broad. Strictly should be avoided same ground lines for designing digital circuits in PCB because digital ground lines always has at least a few millivolt of ground noise. Electromagnetic. Normally, digital equipments are well shielded because aluminum casings are used which shield off all disturbances except low frequency electromagnetic disturbances. Supply cables are infected with high frequency pulse type noise. This type of pulse noise is carried out into casing by main cable. Filters are required for eliminating noise. Digital system signals are not sensitive to low frequency EM disturbances. So, only aluminum shielding is used in digital systems. Main consideration in digital system designed to avoid noise. In addition to shielding, proper mains filtering should always be employed when operating digital systems in a high noise environment. Keep the distance between ground lines and signal lines low, that is, run signal lines near ground lines both on the PCB and when interconnecting PCBs. In CMOS circuit, signal lines should be near to the ground lines. PCB design rules. PCB design rules for power circuits. Board layout should be considered from the very beginning of the design. The most important rule for high power circuit boards is to know your power path. The location and amount of power flowing through a circuit is a major factor when deciding the IC position and the type and amount of heat dissipation required on the printed circuit board. Many factors affect the amount of layout for a given design. These factors include the amount of power flowing through the circuit, the ambient temperature around the device and the board, the amount of airflow around the device and the board material, and IC density on the board. Component placement. Analog circuits and mixed signal circuit boards generally include high power analog blocks and sensitive digital or low power analog blocks. Begin the layout by designing and placing power blocks. Keep connections in individual power blocks short and wide and ensure against unnecessary ground loops and noise generation. Identify and reduce current loops, especially high current paths. Limit resistive voltage drops and other parasitics between components. Locate high power circuitry away from sensitive circuitry. Use good grounding techniques. Furthermore, avoid collection multiple power components together on a PCB. Placing these heat generating components evenly over the board maximizes the thermal balance of the board and protects the PCB from warping. Efficiently reducing heat on the board also protects other sensitive circuitry and signals during operation. IC and component mounting. As power flows through a circuit, both passive and active components generate heat. Heat generated in passive components and ICs alike must be dissipated to the cooler ambient air around the device. This heat is generally dissipated through the package or through the lead frame of the device. In the past few years, IC package manufacturers have built increasingly thermo-friendly packages. However, even with these packing advances, heat dissipation becomes increasingly difficult as IC continue to shrink in size. Many IC packages and board designs do not leave much room for an external heatsink, requiring another method to extract heat, enter the exposed pad EP. A die inside a package with an EP is directly connected to the EP for optimum thermal performance. Correctly mounting these ICs on the PCB optimizes heat transfer from the package to the board. Heatsinks. Components in the power path can generate large amounts of heat. These components need to dissipate the heat quickly and efficiently to the ambient environment. One commonly used method of heat dissipation is the addition of external heat sink to the board. The purpose sink is to remove heat from a device and distribute it to the ambient air. Generally made from highly thermal conductive materials like aluminum or copper, external heat sinks provide a larger area to dissipate heat and should be placed in the path of airflow, if possible, for maximum dissipation. IC positioning becomes increasingly important when using external heat sinks, and the board must be designed so that a heat sink can be affixed in the proper location. To optimize heat transfer from the IC to the heatsink, you can also use a thermal epoxy to ease the heat transfer between the devices. Heatsinks generally require a great deal of room on a board and may not be appropriate for small and compact applications. When space is at a premium, design the PCB to optimize heat transfer through the board itself. Board layout. Special care should be taken to properly route high power parts between ICs and components. The resistance in copper traces can account for significant power loss and heat generation on a board if not used appropriately. Keep traces between power components short and wide, and use thicker copper traces for high current parts. Board designers can also use large copper planes and wires in the board to remove heat from devices. Large planes increase the available area on PCB for heat dissipation from a device. Ideally, these planes are connected on the top or bottom layers of the boards to maximize the transfer to the ambient environment. However, even internal planes can be used to draw out some power dissipated from devices on the PCB. Wires are used to transfer power from one layer on a board to another. They direct heat from the package board connections to another plane or layer. Multiple wires reduce the thermal resistance from the IC to the dissipating plane. High-density circuits. The calculated density gives a good indication of the complexity of the circuits. Density design rules are required to complete the PCB layout complete successfully. Area is the main factor to construct a high-density PCB circuit. Less area is required for good PCB density circuits. When PCB designers design a density circuits, they have to concentrate on area a board with low density. The theoretical value of density limit for a digital board using ICs in dual inline packages is 0.45 SQ per CE. The 14-pin of chip is separated by 0.25 inch. Density guidelines for PCB design, shown in figure, will pop up. Limitations of manual designing. After completion of electronic circuit design, one wants to implement fast the related PCBs for an early prototype testing. After the prototype testing, modifications on the PCB design are normally required, for which again time must be provided. All operations are carried out by experienced technicians. The problem quite often encountered in electronic industries is the non-availability of sufficient and experienced technicians for layout design and artwork generations. In a time analysis of a layout design and artwork preparations, the total time spent for these two operations, typically 40% for layout design and 60% for artwork design. Therefore, first step in automation will be elimination of manual artwork drafting. Layout sketch is digested and information fed to a photo plotter which directly produces 1:1 artwork on film. In automation design, next step is the use of computer-aided layout design, which still needs the active interference of the designer. Last step in automation is to make even the layout design fully automatic and independent of any interference from the designer. Only large computer systems have the capacity to perform a task.
PCB manufacturing. PCB manufacturing steps. PCB manufacturing step following are the steps involved in fabrication of PCB: base material cutting, drilling, through-hole plating, layer film generation, solder resist film generation, legend printing film optional, laminating, exposing, spray developing, etching process, solder resist masking, legend printing optional. Base material cutting. Base material which is selected based on application may be epoxy resin FR4, duroid of required dielectric constant,
Is cut into the required size.
drilling. Holes are drilled through the board using an automated drilling machine. A CNC drilling or milling machine,
which is controlled by an Excel file with the hole position data and a list of labels of the required drill bits,
is used to drill the holes, to mill certain board contours, and to produce multiple printed panels. The holes are used to mount electronic components on the board and to provide a conductive circuit from one layer of the board
to another.
Through-hole plating. Following drilling, the board is scrubbed to remove fine copper particles left by the drill. After being scrubbed, the board is cleaned and etched
to promote
good adhesion and then is plated with an additional layer of copper.
Since the holes are not conductive,
electrolysis copper plating is employed to provide a thin continuous conductive layer over the surface of the board and through the holes. Layer film. For multi-layer boards, films must be produced according to the number of layers. Powerful software tools generate a plot file whose data control a photoplotter. After developing the films, they have to be inspected under table lamp for any track breaks, line shortages, or missing of any track. Solder resist film. In order to ensure no shortings in the PCB due to formation of moisture or due to spreading of solder leads, the complete board except the pads are to be soldered masked. This is done in CAD design tools and the photofilm is generated in the photoplotter. Then the photofilm is developed. Legend printing film. This is developed in order to ensure ease and fastness during soldering of components.
This is also designed in CAD system
and the film is generated in photoplotter. Laminating. By this process, the drilled and plated through boards are laminated by rolling under pressure a photoresist laminate on both sides of the board. PCB fabrication. Steps involved in PCB fabrication. CAD system. Recommended software for the CAD system is Altium. This software has enhanced features like improved interactive routing, user selectable track width, internal routing loops, PCB routing completion detector, preserving track angles while dragging, designing bottom layer layout, mirror has to done, just by flip and editing the board, etc. Note: minimum track width requirement is 0.2 mm and minimum spacing between tracks is 0.2 mm. CNC drilling milling machine. A computer automated single spindle CNC machine is used which allows direct processing of Exelon, Saib and Mayer drill data or HPGL data for PCB production, drilling, milling, isolation routing, and milling, drilling of holes.
Selection of drill bit is also automated, and the drill bit moves to the corresponding coordinate to make a drill. Likewise, drills of different dia can be made. Photo plotter. With a photo plotter, films are developed for various layers and for the solder mask. Moreover, both positive and negative type films can be developed. This is also a computer automated equipment. It plots images from a CAD database by using Gerber data file on a photographic film. Here, the film is rolled over the inner drum in the plotter. On running the software in computer, the laser diode moves step by step along the rotating drum by means of stepper-motor-driven lead screw. The laser diode moving speed resolution can also be adjusted as per requirement. Film developer. After photoplotting the individual PCB layers, film is produced by a developer machine. Then, under a light table, the film is manually inspected for any track breaks, line shortages, or missing of any track. Here the films are developed manually in a tray. Brushing machine. After completion of drilling, the boards are to be brushed thoroughly to ensure that no stray particles remain on the board. Boards are brushed thoroughly, rinsed and dried by this wet brushing machine. Laminator. This is used to laminate the entire board area with photoresist material. Here either positive or negative photoresist material can be used for laminating the board. We generally use negative photoresist. Lamination is performed by rolling the photoresist coil under pressure on both sides of the moving board by heated feed rollers. However, rotational speed is adjustable as per the requirement. Plating unit. This unit is used for making printed through holes PTH circuit boards where connectivity from top to bottom layer can be made through holes. Here, top and bottom layers are connected by depositing copper in the holes of the board. This unit comprises all the tanks and equipment for degreasing, rinsing, catalyzing, activating, pickling, and plating the drilled and cleaned boards. These processes of degreasing, rinsing, catalyzing, activating, pickling are used for removing grease, oil, dirt, soot, and other contaminants from the surface. After thorough cleaning, only copper is deposited. Exposure system. After fixing layout films exactly on both sides of the laminated board, the light-sensitive cover is exposed by a ultraviolet light in double-sided drawer exposure unit with a vacuum system. After the exposure, that part of the laminate which is not protected by the layout film becomes etch resistant if we use negative film and negative photoresist. Spray developer. After exposing the board to UV light, the PCB is brought into spray developing unit where the board is treated with aqueous alkaline solution like TCl alcohol so that the non-exposed part may get softened. A rotary system present inside the chamber allows the simultaneous treatment of the entire board surface. Foam etching center. After treating the board with aqueous alkaline solution, the PCB is subjected in foam etching center by hanging it into a foaming fluid
usually acids, to etch out the copper from the part of the PCB not exposed to UV. The copper part of the PCB, which is not exposed to UV, gets softened and it is etched by acids. Now the board is ready with printed layer tracks pads which are covered by photoresist. Stripping cuvette. Here the remains of the photoresist material from the layer track pads are removed and rinsed in liquid, usually an aqueous alkaline solution. Oven. After getting the board from the stripping cuvette, the board has to be dried. This is done in oven where temperature is adjustable. Masking and legend printing. The bare copper PCB is silk screened with solder mask, usually green. Sometimes the solder mask is applied by photo imaging or dry film, which is designed to insulate and protect the copper tracks and keep them from shorting together during the soldering process. The solder mask covers the whole board except solderable surfaces such as through-hole and surface mount pads. The solder mask is then dried or cured. The PCB is tinned or plated, that is, solder, silver or gold is applied to exposed pads. The PCB is silk screened with component identification lettering, usually white. The silk screen legend is dried or cured. Any final drilling of holes that are not to be plated through and any extra routing are now performed, and the laminate is cut into individual printed circuit boards. Multi-layered PCB. For fabricating multi-layer PCB, we have to first fabricate corresponding number of double-sided PCBs. For a 4-layered PCB, we have to first fabricate 2 double-layered PCBs, and for 6-layered, 3 double-layered PCBs. These double-layered PCBs are sandwiched one over another exactly with oxidizing agent between them. Then the sandwiched board inserted in the multi-layer press machine. It has a control unit for all pressure supply, press plates and heaters. The large loading door that allows quick and easy access to the pressure part is security switch protected. The unit is controlled by 2 digital and adjustable thermostats, 1 digital timer as well as a pressure valve with pressure meter. 2 strong air ventilators are activated automatically during cooling cycle. After complete curing and cooling, the sandwiched multi-layer PCB is taken out from the press machine, is subjected to masking, legend printing as per requirement. It has got the facility of inspection of photofilm and PCBs under a table lamp with a microscope. Fabrication steps for single-sided PCB. Fabrication steps for double-sided PCB and plated through hole board. Conclusion. In this chapter, we have covered the following in detail: Introduction to printed circuit board, PCB manufacturing process,
Types of PCB: single-sided, double-sided, multi-layer, and flexible. Fabrication process for single-sided PCB, double-sided PCB, multi-layer PCB. Soldering procedure. Repair of PCBs. Design rules for schematic drawings. Design considerations. Layout planning and routing rules. Study of documentation in design and fabrication. PCB design rules. PCB design using CAD. Study of IPC standards.